This time we've got a ball and its height, so how far it travels away from the ground, is given to us by this function. Its maximum height. Well, if you think about a ball and it goes up, it reaches its maximum height when it stops. So when something stops, its velocity is zero, and then it starts to move in the other direction. So that's its maximum height then can be achieved when the velocity is equal to zero. So if that's the case, derive this function to get our velocity. So that just gives us the 15 minus 10t. So after 1.5 seconds, once we solve this equation, we get the maximum height reached at 1.5 seconds. So if that's the case, substitute t back into our function, and the maximum height would be 12.25 meters. So that's how we're going to find it. So keep thinking in the physical terms. What's the situation if it reaches its maximum height? The acceleration's constant. Well, if we derive our function again, so if we derive our function twice and derive that, we get minus 10. So that means it must be constant. So, and if those physics students of you probably looking going, okay, it is then, we know that must be the case because that's gravity. Gravity we're going to take as minus 10 there. Oh, that makes sense. So it's accelerating in the negative direction, so towards the ground. Find the time to one decimal place that the ball reaches the ground. So when's the height equal to 0? So we substitute h being equal to 0. It's a quadratic equation. Again, we're going to get one solution because technically it is a quadratic, so we should get two, but one's going to be negative, so ignore the negative answer there. In this question, we've got a spring, and its displacement is given to us by cos 2t. So here comes our cos functions there. So find the initial velocity and acceleration. We'll derive. So derive it once, we get minus 2 sine 2t, which is our velocity. Derive it again, minus 4 cos 2t. So when t is equal to 0 initially, t is equal to 0, our velocity is 0, but our acceleration is minus 4. So acceleration is reducing, or is reducing the velocity, I suppose, at minus 4 centimeters per second. That's retarding the force at that point, retarding the movement of the ball. There's times when the spring's at rest. Well, velocity's at rest. Velocity is 0 then, when it's at rest. So if we substitute v is equal to 0 and solve minus sine 2t, so really where sine 2t is equal to 0, we start to see a pattern. 0, pi and 2, pi, 3 pi and 2, 2 pi, and so on. Because 2t would be equal to all those, and then we solve that equation. What's the displacement of the spring at these times? So, well, at these ones, when t is equal to pi, 0, pi, 2 pi, then we see that we get a cos of 0, which is 1. If it's at pi on 2, or 3 pi on 2, or 5 pi on 2, we get it being at minus 1. So it's moving between 1 and minus 1, which that makes sense. If you think about the cos of 2t, it shouldn't make too much. It should make sense, and you know the graph of the diagram, graph of the function here. Show the acceleration is given to us by minus 4s. So s double dot is equal to minus 4s. So acceleration is minus 4 cos 2t, as we proved. Is f is equal to cos 2t. Then we can do the substitution. Acceleration is minus 4s. It's what we call simple harmonic motion. That's what we call this. Any cos function or sine function like that would be in simple harmonic motion. It's really an essential one concept we'll explore later.